In this video, we talk about summation notation, sometimes referred to as sigma notation. Why is it called sigma notation? Well, because we are utilizing the Greek letter capital sigma. Sigma means sum of. So, summation notation. The sum of the first n terms of a sequence is represented by the sum from I equals 1 to n of a subscript I. That's the language that we use for the summation. We have the sum from I equals 1 to n of a subscript I is equal to a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a subscript n, where I is called the index of summation. 1, in this case, is the lower limit of summation, and n is the upper limit of summation. So let's talk about I. I, the index of the summation, represents the variable that you are plugging in for to obtain the terms of the sum. Notice in this case we say I here, and whatever variable we have for the index of the summation is the variable that we are plugging in for into our sequence. Notice that we are going to substitute in for the letter I. I is one of the common letters that you will see down here. You will often see K's, J's, N's. Okay, it doesn't actually matter what letter we represent as the index, but just know that that's the letter that you are going to substitute in for. The lower limit of the summation, as we said in this case, which is 1, notice that's the number on the bottom of the sigma, tells you the first value to plug in, giving the first term of the sum. So, because the lower limit here is 1, we substitute in 1 for I into the sequence to give us the first term of the sum, which would be a sub 1. Then we continue to substitute in each consecutive integer. After we plug in 1, we would plug in 2 to get the second term of the sum. Then we would plug in 3 to get the third term of the sum. And we would continue until we get to the upper limit of the summation. So the upper limit of the summation tells you the last value to plug in, giving the last term of the sum. So this number up here represents the upper limit of the summation. I'm going to continue to add terms together until I add the nth term of the sum. That is summation notation. Looks a little intimidating, but at the end of the day, all we are doing is taking the terms of a sequence and adding them together. When terms of a sequence are added together, we generate what is known as a series. Okay, so that's the difference between sequences and series. A sequence is simply a list of numbers, whereas a series is a list of numbers that are added together. Consider the infinite sequence a1, a2, a3, dot dot dot, a subscript I, dot dot dot. Again, infinite sequence, that means I just have an infinite list of numbers. The sum of the first n terms of the sequence is called a finite series, or an nth partial sum of the sequence, and is denoted by the sum from I equals 1 to n of a subscript I would be equal to a1 plus a2 plus a3 plus dot 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 plus a subscript n. So we have a finite series, or an nth partial sum, means that we are adding together a finite number of terms. We start with our lower limit, we continue to add terms until we get to our upper limit. That gives us our sum. Notice that there are a finite number of values that we are adding together. The sum of all the terms of the infinite sequence is called an infinite series and is denoted by the sum from I equals 1 to infinity of a sub I. And this would mean we would take the first term plus the second term plus the third term plus every other term in between, and we would be adding up an infinite number of terms. Notice that we have this dot 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 to represent the fact that we continue to add more and more terms together. All right, so just like we had finite sequences and infinite sequences, we have finite series and infinite series as well. A finite series means we are adding up a finite number of values. An infinite series means we are adding up an infinite number of values. Let's look at some examples. Find the sum by listing out all of the terms in the series. Here we have the sum from I equals 1 to 5 of 2I minus 7. Well, we can list out each of the terms in the sum, and this lower limit of the sum tells us we are going to begin by plugging in 1, and the letter representing the index tells us what letter we are substituting in for. The first term in this sum we would obtain by plugging in 1 for I. That would be 2 times 1 minus 7. Then I would continue to plug in integers. The next integer after 1 would be 2. That would give me the next term in the sum, 2 times 2 minus 7. And notice I'm going to put an addition symbol in between these terms because sigma, that tells me I want to add all the terms together. I would then plug in 3 to get the third term in the sum, plus 2 times 3 minus 7. I would then plug in 4 to get the fourth term in the sum, plus the quantity 2 times 4 minus 7. And finally, to get the fifth term, or the last term in the sum, I would plug in 5 for I, 2 times 5 minus 7. Now notice, in this particular case, 5 is the upper limit of the summation. That tells me where I stop. 1 was the first value I plugged in. I plug in every other integer until I get to 5. The upper limit tells me that's going to give me the last term. So 2 times 5 minus 7 is the last term in the sum. And now all I have to do is simplify these. This gives me negative 5 plus negative 3 plus negative 1 plus 1 plus 3. And if we add all of those terms up, we end up with our final answer of negative 5. Let's take a look at another one. Here we have the sum from k equals 7 to 10 of k divided by k squared plus 1. Now, a couple differences here. One, our letter changed. Instead of i's, we have k's. That's perfectly fine. This is just telling me we are going to substitute in wherever we see a k. The lower limit in this case is a 7. That means I'm going to start by plugging in 7 to obtain the first term in the sum. The lower limit tells us where to begin. Then I will continue to plug in integers until I get up to 10. 10 would be the last value that I plug in to the sum. So that means the first term in this sum would be 7 divided by 7 squared plus 1 plus 8 divided by 8 squared plus 1 plus 9 divided by 9 squared plus 1 plus 10 divided by 10 squared plus 1. And again, this is where we are going to stop because the upper limit of the summation is 10. 10 would be the last value that I plug in for k. Now we can simplify each of these fractions. This leaves us with 7 over 50 plus 8 over 65 plus 9 over 82 plus 10 over 101. And we can plug that into our calculators and get an answer. In this particular case, our calculator is not going to give us an exact answer, but we do get a decimal approximation of 0.47184. Don't be afraid to attempt to hit that math frac button. A lot of times your calculator can spit out a nice simplified fraction, but in this particular case, the fraction would simply be too large. And so a decimal approximation is perfectly acceptable. Find the fifth partial sum of the infinite series. So infinite series implies that we are adding up an infinite number of terms together. But in this particular case, we are asked to find the fifth partial sum. When you are asked to find a partial sum, that just means they want you to add up, in this case, the first 5 terms. Okay, if it were a fourth partial sum, you would add the first 4 terms. If it were a 10th partial sum, you would add the first 10 terms. In this case, because we are asked for a fifth partial sum, we want to add up the first 5 terms of our series. Well, another way of writing this would simply just be the sum from I equals 1 to 5 of 2 times 1/3 raised to the I. Notice all we did is we replaced the upper limit of our summation with a 5 because we want the fifth partial sum. Well, to do so, All we have to do is plug in our values of I to obtain each term in the summation. This would give me 2 times 1/3 raised to the first power. Notice I plug in 1 for I to get that. Plus 2 times 1/3 raised to the second power, plugging in the next integer. Plus 2 times 1/3 raised to the third power. Plus 2 times 1/3 raised to the fourth power. Plus 2 times 1/3 raised to the fifth power. And I stop there because 5 is the upper limit of the summation. And now we can begin to calculate this answer. One thing that we should recognize here is that each one of these terms has a constant multiple of 2 in front of it. And so to actually make our calculation a little bit easier, we can factor out that constant multiple of 2. This would give me 2 times 1/3 plus 1/9 plus 1/27 plus 1 over 81 plus 1 over 243, with each of those fractions inside of a big parentheses or bracket. Okay, so all I did is I factored out the constant multiple of 2 from each one of those fractions, and I've simplified the fractions themselves. 1/3 raised to the first power is 1/3. 1/3 squared gives me 1/9. 1/3 to the third gives me 1 over 27. 1/3 to the fourth gives me 1 over 81. And 1/3 to the fifth power gives me 1 over 243. If we add all of these fractions together and then multiply by 2, hit math frac on your calculator to get the simplified fraction form, we should get our final answer of 242 divided by 243.